Welcome to This Explainer. Today, we're looking at a force that literally dictates everything in our universe. I mean, everything. From the massive, slow orbit of planets, right down to the device you're using to listen to this right now. It's an invisible, dynamic, and totally constant force. It's the ultimate shapeshifter, energy. We're going to decode how it moves, how it changes, and how it ultimately powers our entire world.
But before we really get into the weeds here, I want you to think about this pretty massive, provocative question. Will the universe ever run out of energy? Are we slowly draining some sort of cosmic battery? Keep that in the back of your mind as we go through these concepts, because by the end of this, we're going to have a definitive answer.
All right, here's our roadmap for today. First, the energy of motion. Second, the ultimate shapeshifter. Third, the law of conservation. And fourth, powering the real world. Let's jump in.
Section 1. The energy of motion. Unlocking kinetic energy.
Let's start with a fundamental equation for kinetic energy, which is just a fancy way of saying the energy possessed by moving objects. Now, I know equations can sometimes look like alphabet soup, but let's just read this one as a sentence. Kinetic energy, that's the EK right there, is equal to exactly half of an object's mass multiplied by its speed squared. Basically, it's just a mathematical way of saying that how much work a moving object can do depends entirely on two things: how heavy it is and how fast it's going. And notice how speed is squared here? That means increasing your speed has a massive exponential impact on your kinetic energy. It's a real game changer. You know, this equation intuitively makes sense in the real world, even if you've never actually written it down. Think about swinging a hammer to strike a nail. The hammer has kinetic energy, right? It applies a force to physically displace that nail into the wood. If you use a heavier hammer, so you're increasing the mass, or if you swing it a lot faster, increasing the speed, you generate exponentially more kinetic energy, driving that nail way deeper. That is EK equals 1/2 mv squared in pure action. Section 2. The ultimate shapeshifter. Let's look at the different forms of energy.
Energy is literally all around us, constantly hiding in plain sight in a bunch of different forms, either as kinetic energy, potential energy, or sometimes a combination of both. Radiant energy, for instance, like the light from the sun, well, that's the energy of oscillating electric and magnetic fields. Thermal energy, that's just the random motion of atoms and molecules. Chemical energy is locked tightly as potential energy inside the bonds of molecules. Think about the food you eat. And nuclear energy is that immense potential energy trapped between protons and neutrons inside atomic nuclei. It's an incredibly diverse family tree of energy.
But here's the cool part. Energy doesn't just sit there, it shapeshifts. Take a standard light bulb. It takes electrical energy and transforms it into radiant light, though as a byproduct, it also creates thermal energy, which is exactly why bulbs get hot. Now compare that to an internal combustion engine. That machine's whole purpose is to take the chemical energy stored in gasoline and transform it into the kinetic energy of a moving vehicle, along with, you guessed it, lots of thermal and sound energy. Every machine, every living organism is basically just a complex energy transformer.
Section 3. The law of conservation. Let's look at the 10-meter dive.
Okay, picture this scenario. We've got a 65-kilogram diver doing a handstand exactly 10 meters above the water. Right now, he is perfectly, flawlessly still. Because he has zero speed, his kinetic energy is completely zero. However, thanks to gravity and his height, he has what we call gravitational potential energy. If we do the math, he currently holds 6.4 kilojoules of potential energy. Think of it like two buckets. His potential energy bucket is completely full at 6.4, and his kinetic energy bucket is bone dry at 0. His total mechanical energy is 6.4 kilojoules.
Now, he drops. At exactly the halfway mark, 5 meters down, something pretty beautiful happens. His height is cut in half, so his gravitational potential energy drains by exactly half, down to 3.2 kilojoules. But where did that energy go? It poured straight into his kinetic bucket. Because he's accelerating toward the water, his kinetic energy is now exactly 3.2 kilojoules. If you add those two buckets together, 3.2 plus 3.2, his total mechanical energy is still exactly 6.4 kilojoules. Not a single drop was lost. And then, the exact split second his fingers touch the water surface, his height drops to 0. That means his potential energy is now 0. But he is moving at his absolute fastest speed, about 14 meters per second. That kinetic energy bucket, it skyrockets to the full 6.4 kilojoules. The transformation is totally complete. And once again, the total energy remains an absolutely perfect 6.4 kilojoules.
So, what's the big takeaway here? It's the law of conservation of energy. Energy is neither created nor destroyed.
When it transforms, absolutely nothing is lost. Which actually answers our hook question from the very beginning. Will the universe ever run out of energy? No way. The total amount of energy in the universe is completely conserved. It never changes. It just continuously changes forms, wearing different costumes, forever.
And you don't need to be an Olympic diver to test this out. We see this exact same conservation in mundane, everyday accidents. Imagine a photographer holding a 1.1 kilogram camera about 1.4 meters off the ground. That camera holds exactly 15 joules of potential energy. If it slips from their hands, at the exact split second it smashes into the ground, that potential energy hits zero. But the camera now has exactly 15 joules of kinetic energy. The total energy was flawlessly conserved, even if the poor camera itself, well, wasn't.
Section 4. Powering the real world. Let's talk about going off the grid.
The vast majority of us rely on a massive electrical power grid, that sprawling network of plants, towers, and cables, just to deliver our daily energy. But families like the Jamals up in Sudbury, Ontario, well, they're experiencing some real frustrations with this system. They're facing rising electricity costs and the constant threat of summer brownouts, those really annoying periods where the grid simply cannot meet the peak demand for electricity. So they decided to look into reducing their reliance on the grid entirely.
Now, before they even attempted to generate their own power, the Jamals did something really smart. They tackled their consumption. By installing programmable thermostats, drain water heat recovery systems, ceiling fans, and compact fluorescent light bulbs, they are essentially taking control of their home's energy transformations. They're actively minimizing the waste of thermal and kinetic energy. They're making sure their energy buckets don't leak so that the electrical energy they do pay for is used as efficiently as possible before they take the next big step.
To completely go off the grid, the Jamals are looking to act as their own localized power plants. They're exploring residential photovoltaic systems, better known to us as solar panels, which convert radiant solar energy straight into electrical energy. They're also considering wind turbines, which capture the kinetic energy of the wind. They are literally harnessing that 1/2 MV squared from the moving air we learned about earlier and transforming it into usable electricity right in their own backyard.
Ultimately, transitioning energy sources really just comes down to evaluating trade-offs. On one hand, relying on the traditional power grid provides immediate convenience, but all those miles of transmission cables mean constant energy transformation loss along the way, mostly bleeding out as useless thermal energy, which leaves users vulnerable to those brownouts and steadily rising monthly costs. On the other hand, generating independent renewable electricity involves some pretty significant upfront installation costs for those solar panels or turbines. However, the long-term payoff includes immense savings on bills, freedom from grid disruptions, and the environmental benefit of utilizing localized, clean energy transformations. We've traveled from the microscopic math of a moving hammer to a diver falling through the air, all the way to a family redefining their relationship with the power grid. Remember, energy is never lost, it just changes shape. So, as you look around your home today, ask yourself, what invisible energy transformations are running your life? And who is really in control of them? Thanks for joining me on this explainer. Keep questioning, keep learning, and I'll catch you on the next one.